Speaker is Wasabi, and he's going to be presenting on Can You Hear Me Now? Wireless Communication for Pentesters.
All right, thank you. All right, good morning, everyone. I hope everyone is recovering from everything after last night. So let's get started here. The talk is Can You Hear Me Now? And there's going to be no real voice in this talk. It's going to be data and other forms of communication. And the goal here is to figure out how communication can be used or how mobile IoT communication can be used as a hacker or pen tester's communication backhaul. So, about me. I am a security researcher, which also means I'm basically still just a student. I focus on Internet of Things and embedded devices. I've done this for a few years now, a little over 4 years, which means in the end, I don't know very much. But what I do know is this is something that's very important and it's constantly changing. So the goal here is to show you what's going on, and hopefully next year everyone else can come back and see what you've been working on with these things. In addition to research, I also participate in quite a few competitions, which again means very little, but I have a feel for how the offense and defense scenarios work. So let's get started. The goal for today is to understand what existing technologies exist in the field of wireless communications and pen testing. There's a few, they're very separate but very well-established players. From one side you have things like the land turtle and everything else, and on the other side you have IoT, which would be LoRa, radios, and other things like that. So we'll look at those, where they're good, where they're bad. The other thing we're going to also look at is what types of protocols should we be using for these systems. Now, you may or may not know, with a lot of devices, they have a protocol that's secure. In reality, that's only as good as the devices that you're using. If you encrypt it, what it's doing is it's using a static shared key in many cases, which is very helpful for absolutely nothing. And so if you want to actually do something secure, you want to use this as your C2 channel, you actually have to implement your own encryption, which is awful, but there are libraries that help, and that makes it easier. As the adage goes, don't invent your own crypto. Use someone else who's way smarter than you. So again, we'll look at radios, and then we'll discuss future and related work. So again, the first device, everyone's probably seen this. This is a land turtle. It's great. There's nothing wrong with a land turtle. You plug it in, you can conduct your pen test, you can use it as a remote connect, a pivot. It works fairly good. Some of the newer versions of this, there's a lot of knockoffs. There's the orange turtle that I've seen online. There is the land pie, and every derivative you can think of exists. They basically do the same thing though, which is allow you to connect to a remote network and be a pivot box for you to do your assessment. The only problem with this is it doesn't really support any external communication other than the network you're already using. So that's a problem. If you're going to get detected, it's when you're sending your traffic back over the same network you're trying to conduct a test over. They're relatively obvious. If you look at this, it says do not remove, but if there's any competent IT person, they will probably remove it. The goal is to make something very small that won't get detected, hopefully. Finally, the problem is that there's no passive tap capabilities. You can make it do that, but there's no physical multiple ports. And what do I mean by that? Well, true and proven, the open source community, the open hardware community is constantly improving. This is a GL-iNet, just travel router, but people have used these to turn them into basically the land turtle, but a little better, because it can passively tap. It can act as a bridge and just capture all the traffic going through without anyone being aware, for the most part. And it also has Wi-Fi, which means now you can transmit your data out via Wi-Fi while nobody else is the wiser on the actual LAN network. It's very cheap. One of these costs 20 bucks, and they're very modular. Some of these have actual I/O, so as we'll get to with the actual transmission modules, you can connect directly into them. It's just a GL-iNet travel router. I'll post, when the slides go up, I'll post links with them. So you can see there's some work to do, but there's things that exist. So the next step is if you want to do something with radio, what's the first thing you think of? Well, there's the HackRF and the BladeRF. These are great. They're extremely large and extremely expensive. The HackRF is the go-to. It's very well documented. If you want to do something with radio, you're probably going to start with a HackRF because it's just so well developed into. It only does half duplex though, and we'll get to that in a minute. It's not ideal for speedy communication. You won't probably notice, but it's not the best. Now, what I would consider the best is a BladeRF or a Lime SDR where it does full duplex. The unfortunate part is your price range for all of these is $300 to, in some cases, I was looking online, $800 for just one of these. Now, if you're going to use this as a communication, you need at least two. So that makes that cost really high. Cheaper, if you're going to go this route, is the newer Lime SDR Lite Mini, I believe is what it's called, the Lime SDR Mini. It's $150, which is much more reasonable, and it also still does full duplex. The only downside to this is it only does about 2 channels at any given time, which probably won't be any issue if you're actually using this for C2 communication. So about that duplex. So half duplex you can see in the left, which is where you're transmitting and then you have to wait for the response. It doesn't happen at the same time. Full duplex is where you can send and receive at the same time. It's generally a little more speedy and something we should try to achieve, although in reality, a lot of the IoT communications we'll be looking at don't do full duplex because it's a lot more power use, so they just skip it completely. If you want to get very creative, there's some really interesting techniques that people can do. I don't know how legal these are. You can communicate over ham radio networks. D-Star APRS, you can get a little tiny node transmitter for those that are tiny. They fit in your pocket, and they will transmit a small message at any given time. And because it's ham radio, you can relay 2 places. I have obviously not tested this because using ham radio for things like that is not clear on where the legality is, and I'd caution to say it's illegal. But it is something that can exist. And then there's just true and proven packet radio. Packet radio has been in existence since the 80s, if not earlier, with full mainstream use. The police have been using it for that long. It's well developed. You can use it pretty much anything. There's so many different protocols. You can use them on different bands, frequencies. So there's a lot of stuff you can use with. But the problem is, it works great out here, but what about here? Now, you know, if you're in an office building, you just end up looking creepy with the little radio walking around, and you're more likely to get caught. But thankfully, we have a solution to that, and that is devices. IoT has been an explosion. How many people here have been working on IoT in some form or another? Okay, actually not as many as I expected. Okay. So IoT is very insecure, but what it has allowed us to do is get very cheap modules that allow us to do software programming on them, and then also use them as either radios or anything else we want to do, but extremely cheap. You can pick up most of these for less than 20 bucks, and you can get a bunch of them. So the general goal is radio, what I/O do you want, more radios, how low power do you need to go, and just radios. So we're going to do some science now. The first part is we have to get our data out. If we're going to be using these as C2 communication channels, it's completely effectively useless if you can't get your data out. If best effort is you have nothing, then it's not very good at all. You might as well just use the old Ethernet and you're good. But we can try things. So the first thing is, if you're going for low range and cheap, you have the Zigbee protocols, which are great, but the problem is Zigbee does not allow for range. It gets hit by walls. Walls, it will not penetrate, so if you're in an office building, you're done. But there are other options. You have Wi-Fi. You can run your own Wi-Fi. You can build mesh networks with the ESP modules. They allow for doing a mesh network, so you can relay data between them, and it's relatively secure. So that's a very good option. They're not all that power efficient, so if you're running on battery to make the mesh, you have to keep that in consideration. And when we're building something on our own, you don't want to go this route. Well, this is an extremely cool project. This is the Wi-Fi Ducky. The only problem with it is it looks a little dangerous. And if somebody were to see this, if you're on a legitimate pen test, you're probably going to get this dance crew. And you don't want this dance crew. So we need something a little stealthier, which comes into the microcontrollers. These are all in one packages. Depending on what you want, you can get a system on a chip, which I'm going to classify as running Linux, or just a microcontroller, which you flash your own firmware on, and it'll work. The true and proven radio modules, which most badges are using nowadays, is HopeRF. These are the HRF I'm blanking on the label that they have, but they're very common. RFM, there we go. These are very common. They're very long range for their cost, and they're pretty good, and that's the bottom one. So you can use those as mesh as well. But we want to get range. So how do we do that? So in general, if we're going to be making something with a microcontroller, the more data you send, the more time and power you're going to use. The more data you transmit, the longer it's going to take to verify the data and transmit it back. When you're using radios, you are limited to the amount of data that you can transmit, especially on IoT modules, where the size is in bytes, not megabytes, which is perfect if you're going to be using it as a serial communicator, where you're just trying to get into the device you're using, but maybe not such a good idea if you're trying to exfiltrate or use anything for large amounts of traffic. So power management, if you're doing a mesh, you also have to keep that in mind. But since I'm not sure where everyone's at with radio, we need to look at how radio actually transmits data. So the basics of digital radio, you can see on the screen. It's a little dark, unfortunately, here. But there's a bunch of different protocols. There's ASK and FSK and PSK. Wi-Fi uses the same methodologies. But the general idea is when you're sending a high signal, it'll go either low or high, and based off of what you're getting beforehand, it will decode it. It's a little fancy. It requires timing and all sorts of other things like that, but this is how we're going to do it. And the easiest way and what most cheap radio modules use is ASK, so that's what we'll be mostly sticking with today. All right. So the radios were tested by doing a repeated 1,000 packet module test. When I got each module, I would start being in the same room, very short range, and progressively getting farther, where eventually I was in and driving away from the radio module. Those tests were all outdoors, but it gets a good idea of the actual range. The same messages were transmitted. I wasn't testing serial, so this was just to test the range. And we're back to Wi-Fi. It is, as much as it's obvious in many cases, it's one of the cheapest and easiest to use modules. These ESP8285s are tiny. They're smaller than the 826s, and they have all the same I/O capabilities. They also have built-in memory, so you can use these as little battery-powered drops anywhere you want to go. They can do whatever you want since they have full I/O capabilities, and they can be purchased in bulk. And unlike a lot of the other radio modules, because they have to operate on Wi-Fi, they're fairly consistent, which is a big problem with buying modules that are cheap or radios. You will find that if you buy a pack of any radios, they will end up not being the same. You can't communicate to them or receive from them. So Wi-Fi is good in this case, but they are fairly power inefficient and short range. The maximum range you can get is about 500 feet on an ESP module. I've heard people say they can get up to 1,000, but let's see how realistic that is. And then there's the ESP32, which is on everyone's badge this year. These are a lot more powerful. They're dual core. They have an actual low power core, which is a very neat idea on a microcontroller. I know we're not doing just microcontrollers for this talk, but the idea of a low power core is that if you want to use this device, but you need it to go into a sleep state, the low power core can remain operational, detecting when certain conditions are met, and bring the rest of the system online, which is a very good opportunity to then trigger something else, transmit your data out. It can be logging data until you need to send it out. whatever you need to do for your situation, it can basically monitor and then trigger the full cores. So that's really cool. The other options are the WIST and WISP modules. These are more, this is what you see in the Amazon dash buttons, but their cores are a little more, oh, okay. The range? 500 feet is general what I've seen. People have said they modified theirs to get about 1,000 feet with the right antenna, but your mileage will really vary. So the WISP and WIST devices are very good. It's just there's not a lot of documentation. If you're trying to build something quickly, you don't want to be spending time figuring out the tool chain and all the other components to get it running. You want to deploy and be done. So those are options, but again, they take a lot more effort to deploy. And then we get into LoRa. How many people here have heard of LoRa radios? Okay, more people than have heard of IoT, which is very strange. So LoRa stands for long range something. I always forget the name. It's just a modulation. It's not an actual protocol. If you want to do the protocol, it's LoRaWAN. These are sub-gigahertz, so they have a little more range. The higher you go on frequency, the shorter the distance you can transmit it. That's why Wi-Fi doesn't go as far. They're licensed, so you're going to have to pay a licensing fee when you buy it. It's not very much, but they exist. They can, on top of the modulation, you can put any protocol you want. Two very common ones are the LoRaWAN and Haystack protocols. You don't have to do that, though. One of the neatest things I've seen is somebody was using LoRa to do custom satellite transmissions, and they were getting a huge amount of range with the custom modulation, or the custom protocol on LoRa. By itself, it can get about 2 miles in range, and you can mesh them together based on whatever protocol you're using. So this is a very good opportunity to create a star network where you're actually linking multiple nodes together and then having something get the data out. The data transmission rates on this are very low, but they're consistent. So that means you may not be able to transmit a live feed, you may not get serial, but you can get data out. And as long as you're monitoring that data, you will consistently get the data. You can have error checking and all sorts of things. The other problem with these is if you buy them online, you have to verify the license band, assuming you care about that. They come in different license bands for whichever ISM band, which is the international unlicensed bands in a region. You can get one that's not licensed for your region, the US, or wherever you will be at. And that becomes a problem, so make sure you consider that. So that's a bit about LoRa. The WAN part, again, this one, it says it's encrypted. There is an encryption core usually on these chips. The one that the set that I got from China had a static key set for the software that I was using. Luckily, you could change it. They're very good to just join up. LoRaWAN is, again, it's licensed. You're going to have to pay, but it's auto-join and auto-receive. So in theory, much like APRS, if you're familiar with ham radio, once you join the network, once you're transmitting, any node that receives that data will send it up to the internet, and then you can pull the information down later. So that means even if you're not in range anymore, if anyone is in range, you can use that. They support periods of polling. There's 3 different modes. The first mode allows you to transmit up once every so often. The other one has transmit back and forth, and the final one is basically just a standard communication channel. If you're not worried about getting a live communication, the occasional polling and update method is actually very good because this allows you to just leave the node, don't care about it, and it's just constantly transmitting, and you're receiving. And there's a lot of options. LoRaWAN and Haystack go hand in hand. They're made by different people for LoRa. The only problem is I've never been able to get information on Haystack because every time I try to load their website, I get some interesting errors. Yeah. So it exists. I can't tell you more about it still because their website is still down. And if that says anything, it probably means avoid it right now. but it depends. They say they offer better security, but again, I can't verify any of that because I can't connect. The next option on your list of things that you can be looking at is Sigfox. Sigfox is a little disappointing in the fact that it has a module fee licensing and a service fee. So you have to deal with both the cost of using the network as well as buying the modules. But because it is completely proprietary, for better or worse, it has a very long range. If you're not worried about what you're sending and whether it's actually encrypted or who's listening, it has a very low power and high range, up to 600 bytes a second for a very low power module. So those are an option, but again, there's no way to verify what is actually being encrypted on them. Dash 7 is the Open Alliance Home Hub protocol. It exists, but it's meant, much like Zigbee, to be very, very short range. So if you're going to be transmitting data, it's going to be within the same area you're going to be in, which ends up being a problem just like Wi-Fi. Now, if we were to just say the talk was done right now and this was the module to use, this is the module to use. There's many others, but these, in my experience, are probably some of the best radio modules that exist, if you can get them consistent. The biggest problem with buying these modules, you can only pretty much get them from China or other bulk suppliers where there's not a lot of quality control. They are very good. What they are is a serial module. So just like the original ESP module was meant to just be serial, these are serial. They have a small microcontroller in them. We're not worrying about reprogramming them, but these are very good at transmitting. They support add commands. They support actually connecting, doing different modes. They're very, very nice. They can get up to 1,000 feet range very easily. I've seen tests where you can get up to 3,000 feet or more on these. They're very nice modules, very low power. You can drop them into pretty much anything. If you had, let's say, the land turtle and you needed UART on it, you could drop one of these in there and it would work. The structure of a building will degrade the performance, but if you're still just sitting outside or anything like that, you can do that for a pen test. If you're using it for anything else, it works great too. So those are options. It is very reliable, but it needs consistent power. So if you're using a battery, it will not work as well. The next one is the NRF modules. These are very similar to the HC01s. The only problem is the crystals and the chips. They skimp on parts. They're not very reliable. I've seen myself, I bought a pack of 4, and that was the same pack, but the crystals were different in 3 of them. And if you're familiar with microcontrollers, what happens with different crystals means the signal that you're tuning to on each of the modules is completely different than what it's expecting, so you're getting no communication. That's fun if you have a HackerF or something where you can actually test it. For the longest time I didn't, so I actually thought these modules were broken. When I tested them with the HackerF, I was able to see that they were just off frequency. And there's nothing you can do about that unless you replace the crystals. So it's unreliable because of that, but they're good modules. They use SPI, which most microcontrollers or systems on chips will support. And the best part about this versus the HC01s, which are just pure serial, is they support meshing, which means you can actually build a mesh of network devices and connect multiple to each other. And then finally, for modules that are just pure radio that are fairly well developed, the Hope RF modules. Some support LoRa, some don't. The RF69 HCW is a long-range module. There's the LoRa variants of Hope RF modules. They're really good. If you need a radio module for any project, hobbyist or not, these are modules that you should look into. They're just very consistent. They're very good quality. They have very good range. And the range they say is the range you're probably going to get. So when you're looking for a module and you need something consistent, $10 module, good reliability, it's a good option, even if it's not the longest range. These on average will only do about 500 feet, but they're very reliable. Now, we can look at the pure ASK radios. These are cheap. You can get some of these, you can buy these for $1 on eBay, and you can buy as many as you want. I have a bunch of different types of variants that I've seen online. They're all ASK, but they're a little complicated to use. So what happens is ASK, basically you send data in via wire, and the data goes and transmit, and then you receive it the same way. They need 5 volt or greater. If that's not a problem, you're good. But what's going to start happening is the more power you transmit them with, the longer they're going to go. But in general, you're only going to get about 200 feet for these. So they're not very long range. On the upside, though, they do support the virtual wire and radio head modules support, or library support, which means you can use these on anything that supports Linux or Arduino. There's stuff written for this, and their libraries have encryption stuff already written, and it's fairly good. Let's see here. If you're just transmitting, you can just use a transmitter. You don't have to worry about having a transmitter and a receiver. And then I'll mention this quickly. This is Zigbee. If you haven't heard of Zigbee, you don't have a smart home. Zigbee is used pretty much everywhere. If you're trying to just transmit data and not get noticed, and you're in an area where there's going to be smart devices or power, solar is very big on using Zigbee. If you're not worried about getting detected because there's already a lot of Zigbee, or you're trying to sniff, these are very good. Very good. This includes 6LoWPAN. What else? There's a lot of mesh capabilities. And if you're using a module where you need a mesh short range, a lot of devices, and then transmit out only on a few, Zigbee is a good option because a lot of microcontrollers support Zigbee as well as another protocol like Wi-Fi or something else like that. Google's Thread protocol, which is what the Nest uses, is based off of Zigbee, or specifically it's IE 802.15.4. So these are good, but they only get about 100-foot range. Now, you probably are wondering, why don't we just use satellite? I mean, satellite's going to be reliable. You have line of sight to any satellites. You're going to be able to transmit out guaranteed. You'll be able to transmit back. So there's a few companies that do this. There's Iridium, Globalstar, and Rockblock. I always get that one confused. But they're good companies. They have a lot of options. The only problem is they are universally expensive. You're not going to find one that gives you a lot of data. On average, it's $30 for 10 kilobytes of data. So dial-up may be better. They're not very power efficient because you're sending to a satellite, but if you need to absolutely get data out, this is the way to do it. Here's an example of the modules. You can see the satellite transmitter, a super cap. Again, they have to have consistent power and a lot of power to be able to do anything. So, yeah. And then finally, the reason I came up with this talk in the first place was there's a lot of cellular IoT communication methods now that exist, and these are getting to the point where they're fairly reliable in their network. Since they're using cellular, they exist in a lot of places. So here's a lot of them. So when you think of transmission, you usually of cellular, you're probably thinking 4G or 5G, whatever that's going to be yet. That is the go-to for phones. You don't have control over the baseband. Obviously, there's things in the news right now where that's becoming interesting. They require custom drivers to transmit and receive from, usually, especially on Linux. They don't always support @. commands. @ commands, if you're unfamiliar, are ways of communicating directly with the modem and sending data. And some @ commands will actually allow you to post data to a website. It's very powerful, but not everything supports it. And the reason you want @ commands is if you don't want to write drivers, you can just send commands directly to the device and it'll work. And if you can't communicate with the device, then you know there's a problem. So it's simple. 2G and 3G are the next best with @ command support and general carrier support. It's very inefficient on power. It does support @ commands, especially 2G. You can send commands to send text messages. There's specific code or @ commands to send post requests, get requests, any type of request to the web basically at this point. But there's only so many ways you can send data, and how much data you can send is fairly limited. And then we go to the more modern devices, which is IoT. These are Cat 1, Cat 0, Cat M1, and NB IoT. These all support very limited message transmission rates. It's in the 300 or below range. They do not support voice in general. And when you get down to NB IoT, they are very high latency. The NB IoT reference guide actually says that you may be required to wait 10 to 30 seconds to verify there's a response from any communication you send. So it works, it's reliable, and it's extremely small and low power. But if you need a lot of data, again, it may not work. So here's a picture of the data uplinks and downlinks in perfect conditions. Obviously, we are never in a perfect condition. You can see that Cat 4, which is going to be more your 4G, requires 2 antennas. And then you can see full duplex, half duplex. Basically, everything that's IoT related is going to be half duplex because it's just more power efficient. On the upside, though, with these cellular modules, they're very easy to obtain, unlike the satellite or anything else. My favorites are these two because they actually are very easy to work with. I know AT&T is surprising in this one probably, but they are very easy to get reference material from. They have guides, they have hardware, and it's very cheap, relatively speaking. So I'm going to go read. I did some pricing for you. So Particle. They give you a free card, 3 megabits of data included. Let's say you need to use 30 megabytes for the month. That's going to be $8, so not too bad. If you want to go up to a gig, it's $400. Then you go to Hologram. It's $5 for the car, 40-cent service fee plus 1 megabyte. And for a gigabyte, that becomes $600. T-Mobile, they never respond unless you're a large company using tons of devices. They're never going to respond to you. They never responded to me, so as it happens, I never got their pricing. AT&T provides platform development kits. The API access is $10. The service plan is another $25, but that can get you. But that's $30 for 1 gig. So you can see why AT&T is a good bet for cellular communication. And they support everything, 4G, Cat 1, Cat 0. Verizon only supports machine-to-machine, which is okay, but they also are relatively low, but because it's machine-to-machine, that's going to be your NB-IoT and other things like that, where it's very low speed and high latency. And like T-Mobile, they never responded to me, so your mileage will vary. But here's one of the development kits. You can see how small they are, and this one actually comes with a Pi clone, more or less, so you can just develop on that and it deploys. But what we really want here is we want the thing that's stealthy. If you've seen any of my other talks, you'll be familiar with this one. This is my favorite coffee maker in the world. It's the Wemos Smart Coffee Maker. It uses the same chipset as pretty much every router that exists nowadays. So it has the ability to actually have 4 Ethernet ports in theory. But this is nondescript. You can move this pretty much anywhere and deploy it, and then you have, you have, what? That would be good, but okay. And the best part is I was on the last slide. Okay. Wow. Okay, so before my computer decides to shut off again, this is what we're going for, is if you can embed all these devices into something that looks nondescript, now you have something you can move around, use in a pen test or anything else like that, and it allows you to do a lot of capability. So are you going to repurpose? That's an option. Are you going to build your own? That's another option. And if you're not going to be using it for a pen test and you want to just use something for hobbyists, I hope this guide helps a little bit on what types of communication rates you're going to get, what type of power, and go from there. Now, if you want to help or you want to further the knowledge of this, please feel free to contact me, Wasabi at dc562.org, or follow me on Twitter. I'm the Spicy with EY, Wasabi. So that's it. Does anybody have any questions? The serial modules, the RF serial modules, are pretty much the best for using just general communication. They're easy to use. You just have to you have to test them each time. So if you're not worried about testing a bunch of modules and you get enough that have the same frequency, they're good. They just work once they do. But I know that sounds terrible, but when you're trying to get a lot of data out, those support serial, whereas a lot of them don't. And so just playing with them and getting ones that actually support the same frequency, they support the most amount of data in any one given point, except for Wi-Fi, pretty much. So those are my favorite. And yeah, okay. Any other questions, thoughts? All right. Right on time. All right, thank you guys.